the next example. We're going to go over the last of the things. Basically, we're going to look at the calculus of parametric equations and things of that nature. Not complicated, just different. And we're going to establish some rules, and then basically we're going to take those rules and apply them to a very specific type of application that we're going to do next day, and that's involving polar coordinates, which some of you may remember from pre-calc. And it turns out it doesn't really matter if you remember them or not. So here's the idea. I'm going to define x as a function of t. I'm going to define y as a function of t. T is my parameter. So it basically means we will only have one variable in the problem. Now, one of the great benefits of parameterization is I can take something that's not a function, but through the appropriate parameterization, I can have both variables be a function of something. Let's start with something ridiculously simple, like a sideways opening parabola. Okay, we know that x equal y squared. It's going to look something like this. We also know that's not a function. Now, it might be a very useful equation, but it's not a function. And in calculus, we don't love things that are not functions, because right now, the only way we can take a derivative is using implicit differentiation, which I know most of you don't love. And a lot of times it's very difficult to even draw. You know, I can have something that might look like a figure eight, or last day, remember my ninja throwing star that we came up with. Clearly that's not a function. But if I started with this guy here, and I said, well, what if we let y be t, then x would be t squared. And now I've got x and y both as functions of t. Taking derivatives would mean I'm taking derivatives with respect to t. And this actually might present a very, very simple problem. So our goal today is to how to take derivatives when I've parameterized anything. So that's actually not complicated at all. And we're going to go back to the chain rule in Math 150. So if I had something of this nature, if I said y equals f of x of t. Okay, so in Calc 1, we often had parameterizations. For example, you remember things like, you're blowing up the balloon at a certain rate, the related rate problems. How fast is the velocity changing when the radius is changing, and so on. We made all the variables functions of time in that case. So if I wanted to take the derivative of y with respect to t, I know that would be f prime of x of t times dx dt. We did things like that. That's simply the chain rule factor. So if I now said, I'm going to have, rather than write f of x, I'm going to write it as y. So I have y equals a function of x, which is a function of t. So I'm just basically, instead of saying f of, we'll just say it's y. Most of the time in calculus, when we say y, we mean y of x. That's why dy dx is the appropriate notation. So my y is not going to be so much a function of x, but a function of x of t. I can ask the derivative of y with respect to x. I can ask the derivative of y with respect to t. This is basically 4 weeks into Calc 1. This is why you never use prime notation on a variable. It's like, to me, it's scratching a chalkboard with metal claws. I actually have calc students, even Calc 3, who will write something like this. I actually have no idea mathematically what that's supposed to mean. It's the derivative. Really? Y is a function of x and x is a function of t. Is this the derivative with respect to x, or is it the derivative with respect to t? The answer is neither. In fact, the answer is this is 0. In Calc 3, you prove a variable prime is 0. It can't be anything else. It would be impossible for it to be anything else. The exception is if it's the variable prime with respect to itself, then it's 1. But that would only be if you're differentiating x with respect to x. All other examples would be 0. You can't have a variable prime, so their prime notation is just terrible. So if I wanted dy dt, using the same notation, I want the derivative of y with respect to x, and we will write that dy dx. Now I have my chain rule factor, dx dt. Now, this is Calc 1. This is chain rule in Calc 1. This is really, really early in Calc 1. We learn how to do this. This is the formula we're going to use today. But you say, how does this help me today? Because if I have a parameterized function, if x and y are both written as a parameter, and I'm in the xy plane, I still want dy dx. But that simply means that dy dx, if I solve, is dy dt over dx dt. And that's the magic equation. If x and y are both functions of t, then on the xy plane, dy dx is simply this quotient. And that's rarely going to be a difficult thing to do. Okay, so let's do some examples of that. Okay, let's start with something simple. Let's say that x equals 2t squared minus t, and y equals, I don't know, 3t to the fourth. All right, let's keep it simple. I want to find dy dx. Now here's the problem. If I try to write this in the xy plane, I can do that. But that would mean I somehow have to solve for t and then substitute the other variable. I didn't make that very easy on myself. This would be really difficult. Not impossible, but this would be difficult to eliminate the t's and to just write this in terms of x and y. But I don't necessarily have to. So when I go to here, I want to first find dx dt, which would be 4t minus 1. And then I'm going to find dy dt, which would be 12t cubed. Then the answer to this question, look at the form, would be 12t cubed over 4t minus 1. That's it. I don't need the answer in x and y, because if I gave you this parameterization, then for any value of t, we could figure out what the derivative is. Now, if you think about it, even in Calc 1, you found derivatives as functions, but in real life, you never find derivatives as functions. You find the derivative evaluated at a particular location. Okay, so when you're doing estimations with power series, you don't say we're going to estimate the function in general. We said we're going to estimate e to the 0.2 or cosine of 0.1. We do estimations at particular values. So for any value of t, you could tell me what the derivative is. This is a fairly simple one. Let's do one that's a little more complicated. I love using a circle. A circle is one of the best ones to show this with. So let's consider the circle x squared plus y squared equals, I'll say a squared, radius a. Usually we'd use radius r. We could do that. I'll just say radius a. So it's the circle of radius a centered at the origin. I would like to find the slope of the tangent line at every point on the circle. But that's a really difficult problem to do because that's not a function. So in Calc 1, what we did was we said, well, let's write top half, bottom half, find those two derivatives independently and do it that way. That was absolutely correct. So let's start with that one. So the top half would be y equals the positive square root of x squared, of a squared minus x squared. So dy dx for the top half would be 1/2 a squared minus x squared to the negative 1/2 times negative 2x, which is simply negative x over the square root of a squared minus x squared. Okay. For the bottom half, it would be y equals the negative of the square root, right? The positive square root would be that, the negative square root would be that. So dy dx equals negative 1/2 x squared, or a squared minus x squared to the negative half times negative 2x, which is simply, okay, now I have the negative here. So I'm going to write that, I'm going to leave that the way it was, but I'm going to write it as negative, oops. I'm going to write it as the negative x on top over the negative of the square root. I know that's kind of weird because I have the two negatives. So if I look at the first one, you do notice that if y equals this square root, then my denominator is simply y. Now you're not used to writing y's in the derivative, but actually that would be the correct answer because I cannot isolate the dy dx because I have two halves. And over here, you notice my numerator is negative x and my denominator once again is y. So this was negative x over y. Oh, that's kind of cool. If I said, what is the derivative at every point on a circle centered at the origin, at every point, didn't matter if it was top half, didn't matter if it was bottom half, we got the exact same equation, negative x over y. Now, that's very convenient. So let's make sure that makes sense to us. In the first quadrant and in the third quadrant, all my tangent lines should have negative slope. Another way of thinking about that is when x and y are the same sign, that's first and third quadrants, my tangent line should have negative slope. If x and y are the same sign, then this will be a negative value. If x and y are the same sign, this will be a negative value. In the second and fourth quadrants, my tangent line should have positive slopes. So if I'm in the second or fourth, then x and y have opposite signs. So x over y would be a negative number, making this positive. This is positive. Okay. Here, at this point, a comma 0, and this point, negative a comma 0, I have vertical tangents. So my slopes should be undefined. At a comma 0, my y value is 0. Aha, y value is 0. And how about here? Here at 0a and here at 0 negative a, when x is 0, I have a slope of 0. So that agrees with the obvious just looking at it. This was a lot of work. Is there an easier way? Yeah, implicitly differentiating. So let's do that one next. And then we'll do the parameterized version last. And you'll see every way I look at it, I get the same answer, but some ways are a little bit simpler than others. So if I differentiate that implicitly, that means I'm going to treat y as a function of x. So we remind ourselves, when I differentiate with respect to x, this is going to be 2x plus, this is y of x, so it'd be 2y times the derivative, which would be dy dx. Okay, this is function squared, equals the derivative of the constant, which is 0. That gives us 2y dy dx equals negative 2x. So therefore, dy dx equals negative 2x equals negative. Oh my gosh. Same answer, much faster. Yeah, you would always do this implicitly. It'd be so much easier. But what about parametrically? Now, one of the benefits about parametric equations is I don't have to differentiate implicitly if it's not a function, because the individual dx dt and dy dt are usually going to be pretty simple things. Okay, so let's consider, I'm going to erase this for a moment, need the space. If I were to parameterize the circle that I just did, the standard parameterization of a circle, just so you know, let me do a generic thing here. I have x minus h quantity squared plus y minus k quantity squared equals the radius squared. In this situation, I need this quantity here to be a cosine t squared. I need this quantity here to be a sine t squared. And the reason is, if I square this and I square this and I add them, I will get a squared. So the usual parameterization of a circle, okay, x minus h needs to be a cos t. So x would be a cos t plus h. Y would be a sine t plus k. This is the universal parameterization. It's very similar if I want to do an ellipse also. So if I use this model and I'm centered at the origin, okay, if I'm centered at the origin, then the h and the k are both 0. So we will start with x equals a cos t, y equals a sine t. And if it's a circle, that also means that the t would range from 0 to 2 pi. So dx dt, what's dx dt? That would be negative a sine t. Dy dt, a cos t. So finally, dy dx would be the quotient of these two answers. So it would be this over this. Now that's interesting. The a's are going to cancel, and I'm going to get negative cotangent t. Now that's kind of interesting, negative cotan t. What was our answer before? Do you remember our answer before was negative x over y? If I do negative x over y, that gives me the same cotangent t. But this derivative was even simpler to take than the implicitly defined problem. That's kind of cool. Now, what about second derivative? What would the second derivative look like? Well, it turns out the second derivative is kind of tricky. It's not what you think. It's not the quotient of second derivatives at all. So I'm going to show you, again, this one's a little tricky and most textbooks don't do a great job explaining. They'll give you the answer, but you don't always know where the answer came from. So I'm going to rewrite it like this. If I want you to take the derivative with respect to x of y, that's going to be the derivative with respect to t of y over, over dx dt. The ultimate question is, I have y as a function of x, which is a function of t. So x and y are both technically functions of t. I want to do this, and then this is my answer. But you notice how I wrote it, because that's a y and that's a y. I want to set these guys aside. Dx dt is a quantity that's independent of the y. Okay, this is its own thing right there. So I want to differentiate this. I want to do this. So here's how the formula works. Now, if I want, okay, that's our standard second derivative in the xy world. So technically, this is d dx of dy dx. Okay, isn't this quantity on the right? Isn't that what I'm calling dy dx? Okay, so if I want d dx of dy dx, okay, then what I'm going to do is, see that y there? See that y there? I now want to do the same formula, but replacing the y with dy dx. Over dx dt. So I want you to see this. This, by the way, works the same for the second derivative, third derivative, 10th derivative, 53rd derivative. So again, the operator, that's a result. That's my argument, same argument. So now when I make this argument be dy dx, I'm going to put dy dx right here. But when I put a dy dx here, that is the second derivative. So if I put a dy dx right here, then that's the form of the second derivative, which is not an obvious, simple form. But most of the time, this will not be a complicated thing that we're doing. So let's go back now to the implicit. Okay, let me go back to my x squared plus y squared equals a squared circle. We said here dy dx equals negative x over y. Now I want to stay implicit for a moment. I now want the second derivative here. Well, that means I've got to use quotient rule. Okay, y is a function. So if I use quotient rule, let me start by factoring out the negative. So now it's bottom times the derivative of the top. The derivative of the top with respect to x would just be 1, minus the top times the derivative of the bottom, which would be dy dx, over the square of the bottom. Okay, this is just using basic, basic quotient rule. Now, if I stare at that for a moment, what do I do with this? Well, I just substitute this in. Dy dx equals this. Oh, okay. So this is then the negative of y minus x times negative x over y, all over y squared. I have a quotient within my quotient. I don't really like that. So what I'm going to do to make it easier is just multiply top and bottom by y. When I do that, my numerator is now the negative of y squared plus x squared. My denominator is now y cubed. But x squared plus y squared is just a squared. So after all of that, this is negative a squared over y cubed. Wow, that's kind of crazy. Given this circle, the slope of the tangent line at every point on the circle is this. The second derivative at every point on the circle is this. Okay, that's what it is. I actually do this problem in Calc 1. So now what we want to do is use the parameterized version to see what that result will look like. We now know that's the answer. I'm going to erase this now. So when we did this a moment ago, we said, let's call x a cos t, let's call y a sine t. Then dx dt was negative a sine t, dy dt was a cos t. Okay. I'm going to get rid of this stuff because you now have the results. You know where we're headed, basically. So now I want to do the second derivative. Oh, actually, let me write the first derivative first of all. So dy dx, which we said was a cos t over negative a sine t, and that's just negative cotan t. All right, now let's do the second derivative. So the second derivative is going to have the same denominator as the first derivative. So that's going in the denominator. Okay, I didn't change anything, but my numerator is now going to be the derivative of this. So let me write it out. My numerator is this. Okay. Do we know the derivative of the negative cotan, anybody? What's the derivative of the negative cotangent? Holler it out if you know it. The derivative of the negative cotan.
Is it cosecant squared?
Cosecant squared, good. Positive cosecant squared because that negative was already there. So cosecant squared t over negative a sine t. Well, isn't the reciprocal of the sine the cosecant? So could I just write this as negative cosecant cubed by just moving that up top? Sure. Now, isn't the cosecant the reciprocal of sine? Could I, did I lose an, oh, there's an a in there, sorry. Sorry, lost my a there for a second. Hold the phone, did I lose? I feel like I lost an a somewhere or gained an a, hold on. A sine dy dx. Oh no, we got it right, sorry. So this here is going to be, I'll put it as, I'm running out of room here. I don't want to lose that guy because that should still be there, dx dt. So that's, how about negative 1 over a cosecant cubed t, or negative 1 over a sine cubed t. I could also do it that way, couldn't I? Everybody got that? I could do both of these. Now, what did we say it was in XY world? Didn't we say in XY world, the answer was, I believe we said it was negative a squared over y cubed. In XY world, we said that was our second derivative. In parametric world, both of these we're saying is same thing. That's probably cleaner to write it like that. Well, if I replace y with a sine t, a squared over a cubed, same answer. But the parameterized version was actually a bit simpler to come up with. Parameterization, when it applies, when it is appropriate to use, pretty much always makes a problem simpler than it would have been otherwise. So if I have a parametrically defined curve, in other words, x equals function of t, y equals function of t, I'm already given that. I don't have to do anything. Then finding the derivatives is actually a pretty simple matter pretty much all the time. Okay. Now, the coolest shape that I know, the shape we did at the end of last class, my favorite shape, the ninja throwing star. Okay. Let's look and see what that one looks like from a derivative standpoint. So the ninja throwing star, that's what we said, let x equal cosine cubed, let y equal sine cubed, and then we said this. Okay, so I drew a picture for you last day to help make it, a little easier to understand what's going on. And the picture of my ninja throwing star, first of all, we figured out that if I go 1 unit in each direction on the axis, that would represent points, kind of like vertices. Again, if t was 0, then this would be 1, 0. If t were pi over 2, then I'd have 0, 1. If t were pi, then I'd have -1, 0. And if t were 3 pi over 2, I'd have 0, -1. But then the shape of this thing is kind of cool. I have cusps. Oh, that was a lousy one. I have cusps, whether horizontal or vertical. There we go. I have cusps at each of these 4 vertices. Very, very cool shape. But what about the derivatives? I'm guessing the derivatives in between points are probably not that bad, but the sharp points, the derivatives are going to be odd to say the least. So here's what I'd like to do. I'd like to find dy dx. I'm less interested in the second derivative, but I'm very interested in the first derivative. So if we tried to solve and do something Pythagorean, if we tried to manipulate this, this is just not going to work. So what we figured out last day is if I raise both of these to the 2/3 power, then I got x to the 2/3 equals cos squared, and y to the 2/3 equals sine squared. So therefore that equals 1. This would be the equation in the xy plane for this shape here. Now, let's differentiate this. We can do it 2 ways. We can try to solve for y and then do, top, bottom, all that kind of stuff, which would be nasty. Or we can just do it implicitly. Implicit would probably be a better idea, because I also want to do it parametrically, just so we can compare not only the final answers, but the ease in which we acquire them. So let's differentiate both sides here with respect to x. There's a lot of similarities between implicit and parameterized derivatives. So on the left, I would have 2/3 x to the -1/3 plus 2/3 y to the -1/3, and then the chain rule factor dy dx, which is the thing I'm trying to find in the first place, equals the derivative of 1, which is 0. So let me send the x packing. So I have 2/3 y to the -1/3 dy dx equals -2/3 x to the -1/3. Now I need to deal with the negative exponents. That won't be that bad. So I think the first thing I'd like to do is let's get rid of the 2/3. I don't need those. So I'm going to multiply both sides by y to the +3rd. That would mean that dy dx equals the negative of y to the +3rd times this, or simply over this. Okay, so stare at that for a moment, see if that makes some sense to you. Okay. Saying the derivative at every point on my ninja throwing star should look like this. Well, let's see. X equals 0, my derivative does not exist, but at x equals 0, I also have the sharp points. So I'd have vertical tangents. That makes some sense. When y equals 0, my slopes should be 0, which they are in both cases. Oh, okay. Okay, but it kind of depends which direction I'm coming from. Am I going this way or am I going this way? Okay, so ninja throwing star, there's our derivative. Let's now do it parametrically. So let's leave it in its original form. Okay, let me write that off to the side. All right, so now let's just differentiate. So dx dt. Well, that'd be 3 cosine squared t times the derivative, which would be negative sine t. Okay, dy dt. That would be 3 sine squared t times the derivative, which would be cos t. And then finally, dy dx would be this over this with the negative in front. I get some tremendous canceling here. Both, that will cancel with one of those. That will cancel with one of those. The 3's cancel. And it looks like I'm left with a sine on top and a negative cosine on bottom. Well, that's just negative tan t. Oh, that's it. Well, that's pretty simple. I mean, that's a pretty simple derivative if you think about it. Now, I want you to notice, when t is 0, I'm here. When t is 0, tangent of 0 is 0, and I'd have a slope of 0. Now, as t gets closer and closer to pi over 2, I know the tangent of pi over 2 is undefined. Oh, but as t gets closer to pi over 2, what's happening? The tangent is growing without bound. Tangent's approaching positive infinity, but I have a negative tangent. So that means that's approaching negative infinity. What's happening to our slopes? They're getting steeper and steeper and steeper negatively. That's hugely important to recognize. Because then if I'm on the other side, if I'm approaching pi over 2 from the other side, my slopes are getting positive without bound. That makes sense. Okay, so this actually describes the shape much simpler than that one does. Now, how are these possibly the same? Well, what is y over x? Right now, what is y over x? That would be sine cubed t over cos cubed t. And wouldn't that be tan cubed t? So the tangent of t would be the cube root of y over x. Aha, that's exactly what we have. So once again, the parametric form was not only easier to come up with, it's probably better at describing my shape, which is very cool. Now, we're going to change gears. One of the things I'd like to know is, from here to here, how long is that? What is the length of that curve? I have a formula in Calc 1 that I can use to figure that out, but it's probably way too complicated. So now we want to talk about length of a curve, or arc length. And in a Calc 1 class, what I usually like to do is I'll stand in front of the room and say, I think you have 50 something desks in the rooms. And I'm standing in front of the room and I say, I want to get to the back door. Well, I can't walk on a straight path. There's no line segment that I could draw from where I'm standing to the door. There's desks in the way. So when I'm going, I'm kind of cutting in and out of desks, I'm doing a little serpentine as I get through the room. So now that I've gotten to the other side of the room, if I said, how far did I actually travel? So if I took the length of the line segment from me to the door, and then I take my actual path should be a little bit longer, not shorter. So the line segment clearly would be the shortest path, but how much different is it? So that's part of what finding length of a curve is all about. So I'm going to do the Calc 1 derivation really quickly for you so that we have something to work with. And then what we're going to do is the parameterized version of that. I'm not going to hand you a formula and say, okay, memorize this, because then nobody understands what the heck they just did. So the concept of, I want to find the length of a curve. Let's say I'm starting here, and I'm going to here. So this is x naught, y naught, and this is, x1, y1, however you want to say it. I want to find the length of the curve. Well, if I really wanted a crude estimation, this is me, this is the other side of the room, and boom. If I just drew a line segment and I found the length of that line segment, that would be a very, very crude estimator, but I think we all agree that it wouldn't be a great estimator because it's probably too short. How can I make this a better estimation? Anybody? How can I do a better job of estimating from here to here if a line segment is just not that good? Maybe want to try that one? I'd like to estimate this distance from here to here. I drew a line segment. 1.
Add more line segments. If you added
more cowbell, right? More.
Yeah.
What if I went, I go that one, and then that one, and then that one, and then that one, and that one? Would that be a better estimator? Doing a whole bunch of them, would that be better? I think it's obvious, yes. You can smell it, can't you? Smells like a limit. Okay, but a limit of what? Clearly, one line segment is not great, but if I said 10 line segments, you go, you know what? That's much closer. What if I have 100 line segments? What if 1,000 line segments? Each line segment, as they get shorter, the amount of over under, the amount that I'm losing clearly is going away. So what I want to do is just take one of these little things that I just did, one of my little line segments, I want to blow it up. Okay, so here's what we have. This was one of the little pieces of curve, and this was the line segment that I just drew. And this is how we do the problem in Calc 1. Now, for whatever reason, again, I wasn't there when the Universal Math Council decided. Does anybody know what symbol we always use for arc length at every level of math, including three-dimensional Calc 3? What letter of the alphabet do we use for arc length? Does anybody know?
Is it S?
It's S. Well, remember, we use M for slope. So there's really no logic there. Yeah, we use S. We use a little s. And every capacity in math, when you see a little s, it always arc length. Yeah, why didn't we use an A? Well, we're using A for area. Why didn't we use an S for slope? I have no idea. Again, maybe it was Latin. I don't know. But this is the actual change in arc length. We'll call it, it's the ith piece. This is what's called the incremental or differential change. And this is the same notation we used in Calc 1. Remember when we did the tangent line escaping the curve and we used the value on the tangent line to estimate the value on the curve, Calc 1? We do a similar version in Calc 3. The ds was my estimator of the delta s, just so you know from a notation standpoint. Now, that's delta x, that's delta y, clearly. But the cool thing is, delta x represents the change on the curve. Dx would be the change on the line segment. Well, in this case, wouldn't delta x equal ds? In other words, that's the same change for the line segment and the curve. And similarly, dy would be the same. Now, when y is a function of x, we generally will use the d to estimate the delta. In this case, the d and the delta here are the same, not here. So here's our goal. Okay. That's the symbol for, we're using it as an estimator. Eventually there'll be a Riemann sum that involves a limit. That's where the equal comes from. Simple Pythagorean theorem. What is this? Well, we'll use the deltas. Wouldn't that be delta xi squared plus delta yi squared under the square root? Everybody see that? Simple Pythagorean theorem. No big deal. Okay, I've got that picture. I'm going to take this down now. So now we want to manipulate this because eventually we want to take a limit. Well, let me give you some simple algebra. If I said a squared plus b squared and I want you to factor out a squared, how would you write that? If I wanted to factor out a squared. We've done this kind of stuff before.
1 plus b squared over a squared.
Perfect. I want to factor out the delta x quantity squared. So that means that this would be 1 plus delta yi squared over delta xi squared times delta xi squared. Do you all agree with that? All under the root. Now, the delta x represents movement from left to right. Delta x cannot be negative. Delta y can. If my curve is going downhill, the change in y can be negative. But delta x, I'm starting at the left end and ending at the right end. So the delta x's cannot be negative. Why is that important? Because I want to pull it out of the square root. I don't want an absolute value. So let me rewrite this as 1 plus, how about if I write that as the square of delta yi, delta xi, under the root, all times delta xi outside the root. Okay, so this is the length. This is exactly the length of my short little line segments. So here's what we do now. And this is very, very Calc 1-ish, because this actually comes, this is my last lecture of the semester in Calc 1 for anybody who's been in my class. We can now say that arc length can be estimated by the sum from I equal 1 to n of the DSIs. Oh yeah, I'm just going to add them all up. But what am I adding up? This, boy, that looks very Riemann sum. That's where it's going. And before, I think I used x0 and x1, so I should put those in there. There's a boundary. Now's where it gets really cool. We use very calculaic thoughts. I want to say equals. S equals. Well, this is where the limit comes in. S equals the limit as the norm of the partition approaches 0 of the exact same quantity. I'll remind you guys what that actually means. The norm of the partition means the largest such delta x. A partition, when you did your Riemann sums, just a reminder, Calc 1. And you found the area and you subdivided it into a bunch of random rectangles of different sizes. And then you found all the areas and you added them up. That was a rough estimator. The more rectangles, the better the estimator. How do I get an equals? By making the largest width approach 0 means that there's now a new largest width and it's approaching 0. Then there's a new largest width and it's approaching 0. Essentially, if the largest width is approaching 0, then all of the widths are approaching 0. I can't just say delta x approaches 0 because there's n of them and they're all independent of each other. So by saying the largest one approaches 0, that means they're all approaching 0. This is the Riemann sum. We know this went directly into an integral. Problem is what integral? Because that doesn't look like anything yet. So here's the coolest part of the process. Now I'm going to erase the stuff above because I need this space. This is one of the coolest things you do in Calc 1. And unfortunately, what I'm about to show you, I've never seen in a class, never seen on a video, I've never seen in a textbook. Because at this point here, people do what's called little hand waving and little song and dance and say, and here's the formula. Don't ask me why, I don't know where it comes from. I've actually never seen anybody explain the next step, which you all know from Calc 1. I know that the limit of a sum is the sum of the limits. Remember when we did power series, we did the integral of the sum was the sum of the integrals. That's a limit property. So I'm going to rewrite this now as the sum of the limits, but I don't feel like rewriting. I'm kind of lazy. What is the limit of a root? Isn't it the root of the limit? And now I have the limit of this sum, but isn't the limit of a sum, anybody? Keep going on here. Limit of a sum is, you can be unmuted for this.
Sum of the limit?
The sum of the limits, which means, so I have the limit of 1, which is 1, plus the limit of this. Now here's where it gets cool. I have the limit of a quantity squared. That's the same as squaring the limit. So rather than rewrite this 5 times, what I have now is S equals the sum from I equal 1 to n of the square root of 1 plus the limit as delta xi approaches 0 of delta yi over delta xi. And the reason I'm saying delta xi is because I've moved it inside for the one individual term, and now I'm squaring the whole thing. And then on the outside, delta. Okay. Does everybody follow what I did? I took the limit. I'm just using limit properties. But this is why this is so cool. Does that look like anything to anybody? In Calc 1, if y equals f of x, then the limit as delta x approaches 0 of delta y over delta x, we can also write as the limit as delta x approaches 0 of f of x plus delta x minus f of x. Sorry, a little tight there. These are exactly the same statement mathematically. If I'm using y, I write it like this. If I'm using f of x, I write it like this. Does that statement ring a bell to anybody? What is that limit called? It was kind of huge last semester.
It's the formula for a derivative.
Yeah.
It's the definition of the derivative. You're absolutely correct. It's the definition of the derivative. Look at this. The limit as delta x approaches 0 of delta y over delta x. That's the definition of the derivative, which means at this point in the game, I can replace this quantity right here with simply dy dx. That is the definition of the derivative, which is why the formula for arc length you learned in Calc 1, because remember, the Riemann sum gets to go directly to an integral. And it's the integral from x0 to x1 of something dx. But what the heck is my integrand? Well, I'm going to start with the square root. a 1, but a 1 plus what? dy dx squared. This is the formula you learned in Calc 1 for arc length. But unfortunately, a lot of you just were given this formula and told to memorize it because the derivation is usually weak in most calculus books. It's just one of those things. The only thing worse than this is the derivation for surface area. This doesn't even exist in most of the books. They just give you the final formula. But this step is not a leap of faith. This is the whole point. This is the fundamental theorem of calculus, Riemann sum, the whole thing. Now we get it to here. We're like, yes. The problem with this formula is really simple. For most every function that exists, you can state the arc length for me. You just won't be able to calculate it. The problem is you get an integral that can't be integrated pretty much most of the time. Let's do a simple example. So we're doing Calc 1. Find the length. We'll do something really simple of the curve. How about y equals x cubed from 1, 1 to 327. Okay, I want nothing complicated, just a really simple x to a power kind of thing. Okay, so in a Calc 1 class, if you're looking at the problems in the back of the book, most of the problems in this section will say, set up the integral to find the arc length. When I ask this question on the final exam, I'll say, set up the integral to find the arc length. I don't ask you to evaluate the integral, I just ask you to set it up. Why? Well, let's see. What's dy dx? That's 3x squared. So what's 1 plus the square of dy dx? Because this is going into my integrand. That'd be 1 plus 9x to the 4th. Okay, great. My arc length is, because I'm integrating with respect to x, it's going to be 1 to 3. See, I may find it prudent to integrate with respect to y in some cases. And my integrand is going to simply be 1 plus 9x to the 4th dx. Now you're in a Calc 1 class. What do you do at this point? You smile and wave. You're in a Calc 2 class. What do you do at this point? Same thing, because you can't integrate that. Why not? Well, that's my u. I don't have a du. Well, what about trig substitution? What trig substitution are you going to use? We're dead in the water. In other words, almost everything you could write down, you can write down the integral, but you can't integrate it. We just don't have the means. Turns out in Calc 1, there's only 3 problems you can actually integrate. Isn't that crazy? 3. I mean, you can change the coefficients around, but there's only 3 problems you can actually find the arc length to. I want to do one of them just to show you what goes into the process, because it's not trivial. And then we're going to look at the Calc 2 version, which is infinitely superior, because we will be able to do many, many more things through parameterization. So let's Calc 1. Let's find the length of the curve. Of the curve y equals x to the 2/3 from, how about 1, 1 to 8, 4. I'll do that. So if you don't remember, this looks like a cusp. It looks like that on both sides. So I want to go from 1, 1 to 8, 4, basically. I'm going to do from there to there. Okay. Well, if I simply do the line segment, I could give you a reasonable estimator, but it wouldn't be the answer. But drawing the line segment and finding its length is a great way to check my final answer, by the way, because this isn't moving rapidly. I think we all agree that the line segment should be a little bit shorter than the curve, but it's not going to be very much shorter than the curve. So when I'm all done with this problem and I find the length of the curve, it's wise to actually calculate the length of the line segment and compare them. In other words, make sure the length of the curve is a little bit longer, not a little bit shorter or way, way, way different. So like we did in the last problem, we start, this is the order of things. dy dx, that'd be 2/3 x to the negative 1/3. 1 plus the square of dy dx would be 1 plus 4/9 x to the negative 2/3. Now that's what's going to go into my square root, except I don't really like it in that form. So why don't we rewrite that as 1 plus 4 over 9x to the 2/3? Okay. Well, I think we could write that as one quotient. So how about I write it as 9x to the 2/3 plus 4 over 9x to the 2/3? Okay. Not that it's better, but it might be a little easier to write it now. So now I can say that the length of our curve is the integral from 1 to 8 of the square root of this. All right, okay, so we're dead in the water. Well, actually, not exactly, because isn't my denominator a perfect square? It's 9x to the 2/3, but that is a perfect square. Like, what is being squared there? Anybody? What should my new denominator be if I want to simplify this a little bit? Anybody want to try that? What is the square root of 9x?
3 times x to the 3rd?
To the 1/3, perfect. All right, well, okay, I just went from horrible to maybe horribler, if that's a word. Okay, let me erase this. Well, if I could integrate this, that's a big if. I see a quotient, I see a square root on the top. I don't really have a lot of choices for my u because I have the square root of a function. We know from past that it's the square root of the argument, because if the argument isn't an x, that kind of has to be where the substitution. So let's just try it. If I let u be 9x to the 2/3 plus 4, then what's du? Let's see. That would be 6x to the negative 1/3 dx. Yeah, like I have an x to the negative 1/3 just sitting around in the problem, right? Oh, wait a minute. Do I have an x to the negative 1/3 just sitting around in the problem? Yeah, I have a chain rule factor right there. That's why this is one of the forms I actually can integrate, because this is one of the few forms that we get a chain rule factor. So let's rewrite this, shall we? Let me write it as, how about 9x to the 2/3 plus 4 raised to the 1/2 power. Now I have an x to the negative 1/3 dx. That 3 bothers me, okay? So what I do in Calc 1, I say, look, we have to come up with the right coefficient. Let's not try to be clever and manipulate and what fractional multiples, too much thinking. So let's just take this and move them to the outside. This 3 is in the denominator, so it comes outside as a 1/3. Okay. Now, what do I need this to be? I need it to be a 6. So put a 6 there. I've just made this 6 times bigger, so I compensate by that. Now, quick check. 1/6 times 1/3 times 6 is 1/3, and I'm back to the original. Why do I do this? Because now I can do my substitution. Now, this was kind of icky, so if I'm going to do the substitution, there are limit changes that have to take place. So right now we are at 1/18 u to the 1/2 du. Well, that's way simpler. But what are my new limits? I cannot write the old limits. By the way, there is no exception. Even my Calc 3 students, some of them never learned how to do this. They'll write the old limits here. Well, the problem with that is this is a numerical answer. If you put limits here, you evaluate it at those limits. There is no such thing as a substitution back in a definite integral. That step doesn't exist, and nobody was ever shown that. But I find people come up with it all on their own. They put limits here that are not correct, which now means this gives the wrong numerical value. And then they'll say it equals to some other wrong numerical. Don't do that. Yeah. As x ranges from 1 to 8. Okay, when x is 1, the value of u would be 9 times 1 plus 4. That's 13. That's a big yuck. When x is 8, well, 8 to the 2/3 would be cube root squared, so it'd be 4. 9 times 4 plus 4, that'd be 40. Those are kind of goofy limits, but those are my limits. I'm not going to question them. Now, whatever the numerical value of the original one is, I am saying this will have exactly the same numerical value. So now integrate, evaluate. There's no extra work. So that'll be u to the 3/2. 3/2 times 2/3. 2/3 times 1/18 would be 1/27. Evaluated from 13 to 40. So check this out. How about 40 to the 3/2 minus 13 to the 3/2? I'm going to walk away. That's good enough. Oh, well, why don't I write it as 13 root 13? Actually, going backwards if you do that. If you had x to the 4th power, would you write it as x times x times x? No, leave it as an exponent. I might be able to pull something out. Yeah, but these are irrational numbers. Let's just be happy. That's the answer, I think. Let's now do a quick check. But how do I check it if I don't know what the answer is? Well, we don't know what the answer is, but we know what to compare it to. The line segment, like I said before. So let's do a numerical calculation of this. So this is 40 raised to the 3/2 minus 13 raised to the 3/2 all over 27. All right, my calculator says this is approximately 7.634, go as far as you want. This is the answer. There's a good decimal approximation. Now, I said if we find the length of the line segment joining those original 2 points, that line segment should be shorter, but it shouldn't be way shorter. So distance formula, right? 8 minus 1, that's 7. 4 minus 1, that's 3. That's the length of the line segment. It's that simple. That's root 58. How big is root 58? Root 58 is approximately 7.612. Is that good? That's great. That means that our curve was only a little bit longer than the line segment. That gives me faith in this answer, in other words. If that had been bigger than this, then I wouldn't trust it. I think we made a mistake somewhere. Now, this is arc length, but we did it in XY world, and this was a lot of work. What about in parameterized world? Because that is the whole point of this. I wanted to demonstrate to you how you did it. This is a problem that I do in Calc 1 every semester. I'm going to do it in about 2 weeks in my current Calc 1 class. So now let's go back to our original picture. And now we can save some tremendous time because we already did the setup. Okay, we know that delta SI can be estimated by DSI, which is equal to the square root of this plus this. That's not in question. We already did that. So now I'm going to show you a different algebra trick. One that you probably aren't as familiar with, but maybe you have done in other areas. All right, I've got a squared plus b squared. A little while ago, I asked you to factor out an a squared. Okay, I want you to do the same thing, but this time I want you to factor out a c squared. There's no c though. I don't care. I want you, if I gave you a number, 6, I want you to factor out a 1/3. Well, then I'd write 6 equals 1/3 times 18. Oh, yeah, I can always do that. Doesn't matter what it is. As long as it's not 0, I can always factor something out. What would that leave me with? Anybody want to try that? I'll do that part. So what's going to go here?
The a squared divided by c squared.
Yeah. Oh, okay.
And then, yeah.
You agree? Oh, okay. So that's what I want to do here, but I don't want to factor out an x squared or a y squared. I want to factor out a delta t squared. I want this to look very parameterization-ish. So how about if I factor it out, and I'm going to do the same thing. And I'm just going to go ahead and fast forward, and then we pull that guy out. Well, it's clever algebra. It's not like life-changing. Let me rewrite that as delta ti over delta xi quantity squared, delta yi over delta ti quantity squared under the square root. Now you know where this is going. There's going to be a Riemann sum. There's going to be a limit. Boom. I'm going to fast forward now and say this is equal to the limit as the norm of the partition approaches 0 of the sum of all these guys from I equal 1 to n. You knew that was coming. Okay. Because I've already done it once, you know exactly how we got from there to there. Now, don't worry about the range of values for t, because that's probably given. Now, as I move my limits, whoops, did I write that correct? Whoops, you know what? I wrote this one backwards, didn't I? Sorry, these are delta x's on top, not on the bottom. That's a big X. Now, when I move that limit on the inside and I say the limit is delta t approaches 0 of this, what is that going to become? Very specifically, what will that term become when I take its limit? Think of what we did with the x and y. The delta y over delta x became dy dx. What's this going to become? I'm going to go t0 to t1. That's going to become dx dt. That's going to become dy dt for the same reason as before. I'm going to move the limit on the inside. The norm of the partition in this case would be the delta t. So I have the exact same curve that I did before, exactly the same curve. But now I'm saying, what if I parameterize that curve? X is a function of t, y is a function of t. I don't even have to explain why I'm doing that because we know algebraically this is equal to this. As long as delta t is not 0, which it is not going to be, this is absolutely equal to this. So when I take my limits, I produce a different integral. But I produce an integral that is far more likely to be able to be integrated. Plus, I can do this for things that are not necessarily functions. And that's really cool. Okay, so that's the formula for the parameterized version. And it turns out next semester in Calc 3, we start with this guy, but then we do it with a third variable, which is way cool because it's not hard. All right, so why don't we do the following? Let's find the length of the curve. How about x squared plus y squared equals, I'll use r this time. Okay. Let's just find the length of this particular curve. What am I asking you to find? What's another word I'm asking you to find? The length of that curve.
The circumference?
Circumference of that circle, exactly. Oh, I already know the circumference. Can you show me how you know the circumference? I was told the circumference in 4th grade. Do you remember in Calc 1, hopefully in your class late in the semester, and you did things like you found the surface area of a sphere and things like that, but it required calculus? Now, it turns out every important geometric formula involving curves, like circles, ellipses, things like that, spheres, every single one of them requires calculus in order to find. You can't tell me you know something if you can't show where it came from. The results you were told were correct, but where they came from wasn't just random. It actually requires calculus. So how the heck am I supposed to do this? This is a circle. This is a circle centered at the origin. All right, why don't we do this? Let x equal r cos t, y equals r sine t, and t will range from 0 to 2 pi. Why don't we do this? Let's do what we just did and use the length of the curve, the parameterized version. Okay, so what is dx dt? That'd be negative r sine t. dy dt equals r cos t. So what's going to go under the root is the sum of the squares. So I'm going to write it out. dx dt squared plus dy dt squared under the root is r squared sine t plus r squared cos t under the root. Can that be reduced? Does that reduce? Anybody? I'd like to reduce that if I can. I don't want to write an integral of that. That's just too scary looking.
You could factor out the r squared.
Okay, and then what will that leave me with ultimately? Sorry, those are squared. Sorry.
Oh.
Sorry.
Oh, 1.
Sorry.
Right.
Yeah, it's squaring those guys. Sorry. Cos t squared. So after all said and done, isn't that just r? Because it's under the square root. Right? R squared sine squared plus r squared cos squared is r squared times sine squared plus cos squared, which is r squared times 1, and then the square root. Remember, r is the radius of the circle, so r can't be negative. So that means, little drum roll, the arc length is the integral from 0 to 2 pi of r dt, which is just rt from 0 to 2 pi, which is 2 pi r, and that's where it comes from, folks. Not possible to get that without doing what we just did. Okay, the circumference of the circle has to be integrated. And this is one of the reasons I tell people you can't use degrees in a calculation, because degrees aren't a measurement. Pi radians is a measurement, and it also has to do with length. Pi is kind of a unitless thing. The radius has the unit, so this is a length. But this is just so cool that you can do stuff like this. So the question I always have to people that I want to know this. Okay, there's a few things I want to know. I want to know where's the other focus in our galaxy, or I should say in our solar system, you know, but more importantly, where's the focus that's bringing Halley's Comet back every 86 years? Okay, it's one of these things I want to know before I die. But I'm far more interested in how the Greeks knew this in the 4th century BC. See, people don't realize the Greeks knew about pi. They knew about pi. They wrote about pi. They have documents. The Greeks knew the area of a circle, and the circumference of a circle, and the surface area of a sphere, and the volume of a sphere. They knew these in the 4th century BC. Calculus was invented in the 17th century AD, 2,000 years later. How did the ancient Greeks know stuff that could not be derived or proved for 2,000 years? Anybody know? I think I have the answer, by the way. I think it's a really simple explanation. Okay, you guys have all seen Men in Black. It's the same place Velcro comes from. Anybody? Pyramids. Where does all that kind of stuff come from? Come on, you guys watch television and movies. Where's the unexplainable stuff all come from? Or where's it all attributed to? So the ancient Greeks knew mathematics that took us 2,000 years to actually prove and derive and everything else. Oh, you guys are no fun. Aliens, obviously, right? They were in cahoots with alien cultures who were feeding them information ahead of time. And, they didn't understand the calculus because that took a while. No, I find that to be one of the most fascinating facts is they knew this 2,000 years before the ability to actually derive this, period. There was nothing in between. There was not even a suggestion of something in between, which is really quite amazing. So this formula that we just used, it's not going to be easy for all problems that exist. No, but in Calc 1, we were very limited. First of all, we can only do it on functions, and we can only do it on very few functions. Now, if I have a parameterized curve, it doesn't even necessarily have to be a function. I just did a circle. But it is often the case that when you do this, your resulting integrand, your square root of whatever it is, may be evaluated. Not always. It may be. All right. This now ends the material that will be on our next exam. So I will be posting the practice test pretty soon. We're at the end of week 13. So of course our test is at the beginning of week 15. Now we only have a handful of quizzes and things left. In fact, in terms of lectures, we have exactly 2 lectures left. Okay. And those are going to involve polar coordinates, which are some of the most important things we do in this class. So in the remaining 3 weeks, there's 2 lectures, there's 2 exams, final, and 2 reviews. So hopefully you guys are in a really, really good place. Plus, if you go to Canvas, like I mentioned before, and you hover the cursor over your total, you can see exactly where you are and exactly what you need to achieve that goal, if that goal is achievable before the final exam, which I hope it is for anybody still around. All right, let's take a short break. Today we record